Quantization is one of the most practical ideas behind fast AI inference, and it is especially important when a model has to run cheaply, quickly, or on limited hardware. Start with the simple picture. A neural network is mostly a huge collection of numbers, weights, activations, intermediate values, and sometimes cached attention values. During training, those numbers are commonly represented as 32-bit floating point values. Float 32 is flexible and accurate, but it is also expensive. Every number takes more memory bandwidth becomes a bottleneck, and arithmetic can be slower or more power-hungry. Quantization asks a very direct question. After the model is already trained, do we really need every value to have that much precision during inference? Very often, the answer is no. We can represent many of those values with fewer bits and still keep the model useful. So the big idea is not mysterious. Quantization is controlled compression of numerical precision. The core idea is to map continuous floating point values into a smaller set of integer buckets. Imagine you have many decimal values spread across a range, like -1.2, 0.03, and 2.7. Instead of storing the exact decimal value, we divide the range into discrete steps and store the bucket index. int8 is a common example because it uses only 8 bits, so it can represent 256 possible integer values. That sounds tiny compared with float 32, but for many neural network layers, the exact decimal is less important than preserving the rough relative structure. If 2 weights were small and 1 weight was large before quantization, we want that pattern to mostly survive afterward. This is why calibration matters. We need a representative sample of real inputs to estimate the ranges activations usually take. Bad calibration can squeeze important values into too few buckets or waste buckets on rare outliers. The mental model is the affine quantization formula, Q equals round of x divided by scale, plus 0 point. Here x is the real floating point value, Q is the integer value we store, scale controls the size of each bucket, and 0 point makes it possible for real 0 to line up with an integer value. That last detail matters because 0 appears everywhere in neural networks, especially with padding, sparse activations, and operations where exact 0 should stay exact. To approximately reconstruct the value, we use x hat equals scale times q minus 0 point. This reconstructed x hat will not usually equal the original x exactly. The gap is quantization error. The whole engineering problem is choosing scales, 0 points, and sometimes clipping ranges so the error is small enough that model quality remains acceptable while memory and compute improve. The trade-off is where interview answers often become stronger. Quantization gives 3 major wins: smaller model size, lower memory bandwidth, and faster arithmetic when the hardware has efficient integer or low precision kernels. But none of those wins are automatic. If the target hardware does not accelerate int8 well, the theoretical speedup may not appear. If the model has layers that are very sensitive to precision, accuracy can drop. If activations have large outliers, many normal values may be forced into a narrow part of the bucket range. That is why real systems use variations such as per-tensor quantization, per-channel quantization, mixed precision, and keeping the first or last layers in higher precision. The practical answer is, quantization is a speed and memory technique, but it must be validated on real tasks and real hardware. For interviews, organize the answer around deployment. First, define quantization as reducing numerical precision, usually from float 32 or float 16 to int8 or another compact format. Then explain scale and 0 point. Then mention post-training quantization, which is fast because it uses an already trained model plus calibration data. Next, mention quantization-aware training, where the model is trained or fine-tuned while simulating quantization effects, so it can adapt to the rounding noise. QAT usually takes more effort but can recover accuracy when PTQ is not enough. Also mention that weights and activations can be quantized differently, and that large language models often use weight-only quantization to reduce memory while preserving acceptable quality. A strong interview answer always ends with measurement, compare latency, throughput, memory, and accuracy before and after quantization. So the crisp summary is this: quantization turns high-precision floats into compact integer buckets using scale and 0 point. It saves memory and can speed up inference because less data moves through the system and hardware may run low-precision math faster. The cost is rounding error, possible accuracy loss, and extra care around calibration, sensitive layers, and hardware support. If you need a one-sentence interview answer, say, quantization is a controlled precision reduction technique that trades a small amount of numerical accuracy for faster and cheaper inference. Then give the formula, name PTQ and QAT, and say you would validate the trade-off with real evaluation data. That answer shows both the math and the engineering judgment.